and welcome to our continuing lectures on climate dynamics, climate variability and climate monitoring. In the last few classes, we had been discussing the concept of dry and moist adiabatic lapse rates, the concept of potential temperature for dry air and saturated air, and use those concepts to understand what are the conditions that would ensure an unconditionally stable atmosphere where there won't be significant convection currents and associated weather disturbances, an unconditionally unstable atmosphere where you will have convection currents and strong weather disturbances, precipitation propensity, etc., and a conditionally stable atmosphere which, when the atmosphere is dry, is stable, and when it reaches saturation conditions becomes unstable. All of these conditions and the associated expressions and derivations we have done in the last few classes. Here we will wrap up our discussion on atmospheric stability by looking at the comparing how a parcel of air's temperature changes with altitude as it is moving up in an adiabatic process, and we will compare between the case of a parcel of dry air and the case for a parcel of moist air. Okay, and we will see the impact at different latitude values. Okay, so this figure here kind of shows this impact. Here, what we are seeing here is a parcel of air which at different temperatures near the surface. Okay, so we have on the left hand side the significantly cold parcels of air which begins at an initial temperature of 0 degree centigrade, 10 degree centigrade or minus 10 degree centigrade, some things that we will encounter in the high latitudes, versus hotter parcels of air like air parcels that are starting at 20 degree centigrade or 30 degree centigrade near the ground, as would be typically encountered in lower latitudes like near the equator. Secondly, we are comparing the rate of change of temperature of these parcels of air with as they rise adiabatically with altitude between two cases. In one case, the parcel of air is dry, so there is no water vapor in it. In another case, the parcel of air is saturated with water vapor. Okay, what we saw is the moist adiabatic lapse rate is smaller than the dry adiabatic lapse rate. So, a dry parcel of air will cool much faster than a moist parcel of air. Okay, here the dry parcel of air's temperature plots are given by the dotted lines, and you can see, and the moist parcel of air's temperature profile with altitude is shown by the solid lines. And we can see for warmer air parcels, the differences quickly become very significant. So, consider a case where we have a dry parcel of air that is starting at 30 degree centigrade at the sea level versus a saturated parcel of air that is also starting at 30 degree centigrade at sea level. As it rises, because the saturation adiabatic lapse rate is much smaller than the dry adiabatic lapse rate, the dry air cools much faster. So, by 2 kilometer altitude, the dry parcel of air's temperature has decreased from 30 degree centigrade to say about 18 degree centigrade, whereas the moist parcel of air's temperature has barely decreased by say 3 degree centigrade to about 36 or 35 degree centigrade, 26 or 25 degree centigrade. Okay, so we are already seeing more than 7 degrees difference in temperature with a rise of 2 kilometers, and this difference continues as we go up and up. So, at 8 kilometers, which is near the top of the troposphere near the equator, at least 8 to 12 kilometers. So, near the 8 kilometer region, that same parcel of air has now cooled to more than minus 50 degree centigrade, whereas the moist parcel of air has cooled to only 10 degree centigrade. So, a 40 degree centigrade temperature difference has accumulated between the dry parcel of air and the moist parcel of air by the time they reach near the top of the troposphere or top of the convection cell. So, you can see that there are large differences in temperature between a dry parcel of air rising up and a moist parcel of air rising up, and hence the extent of water vapor that is present near the surface, especially in the hotter regions of the earth, matters a lot in determining what is the temperature of the convection cells at the top of the troposphere. If it's a extremely dry region like in a desert, you will have extremely cold temperatures near the top of the troposphere, whereas if it's a moist region like over the ocean in the equator, you will have significantly warmer air currents rising to the top of the troposphere. Okay, that is one point. Another point is the difference between the fate of parcels of air that are rising from much lower temperature conditions. So suppose you are near the higher latitudes, so say 60 degrees or 70 degree north latitude, where it's quite cold, and say the parcel of air's initial ground temperature is 0 degree centigrade. And now we are looking at the dry parcel of air, which is the dotted line, and the moist parcel of air, which is the solid line. And here we can see the temperature difference between these two remain quite small at these cold temperature conditions. And the reason is because the air parcel is already quite cold, its ability to hold water vapor is much lower at these low temperatures. It's exponentially less based on the Clausius-Clapeyron equation. What this means is there isn't much water vapor to begin with, which can condense and release latent heat, which is heating up that parcel of air and decreasing the saturation adiabatic lapse rate compared to the unsaturated adiabatic lapse rate. So the temperature differences are small because the difference in gamma S and gamma D are also quite small. So you can see this point if you look at the expression for gamma S. So this is the expression for gamma S in one condition. We have also given an alternative expression in the previous case also. And here what we see here is that the difference is an important point here is the rate of change of the omega S or QS term, the relative humidity or the specific humidity term, with dT, rate of change of temperature. And if you start at extremely low temperatures, this gradient is much lower. Okay. So that is an important point that needs to be kept in mind, that if you are starting at very low temperatures, then the difference between the moist parcel's temperature and the dry parcel's temperature is not that much. Okay. Now, what happens then typically is that air parcels rising near the equator are much hotter than the air parcels rising near the high altitudes like 60 degrees or 70 degree latitudes. Therefore, the temperature difference between an air parcel at the equator and the air parcel at high latitudes may be say 30 degrees near the ground. So this is say 30 degrees and this is 0 degrees. So this is at 60 degree north latitude and this is 0 degree latitude. The initial temperature difference is 30 degrees. By the time you reach 7 kilometers, okay, this air parcel, even if it is moist, has attained a temperature of minus 6 degrees centigrade, whereas the moist air parcel starting from the equator has cooled only slightly and it reached a temperature of merely 15 degrees centigrade at the same conditions, 15 degree or 10 degrees centigrade at the same conditions. So what started as a temperature difference of only 30 degrees centigrade has gone into a temperature difference of 70 degrees centigrade between the air parcel at 7 kilometers above the surface at 60 degree north latitude and a similar air parcel rising from the equator. Okay. So the temperature gradient at high latitude, at high altitudes between the equatorial region and the Arctic region is much increases as you increase in altitude. So near surface, the air, if the air temperature difference is certain delta T, it may become 2 times or 3 times that delta T as you go up in altitude. Okay. So these considerations have an important impact in determining the temperature gradients in the upper atmosphere as well as the associated wind patterns in the upper atmosphere. Okay. So these are some of the ideas that come up because of these differences in the adiabatic lapse rate. Okay. Now, how does this impact, how does these things change because of global warming? So what we can see is increased surface temperature and increased evaporation from warmer oceans will result in hotter and more humid air at the surface. So the air will become hot and more humid near the surface compared to what it was before the anthropogenic global warming kicked in. Okay. Thus, conditionally unstable regions will have a greater tendency to tip from a stable to unstable regime, because air pulses are likely to be holding more water vapor and hence likely to tip from a stable dry system to a unstable saturated system much more easily. So you are likely to get much significant weather instabilities and precipitation events due to the rising temperature, especially in regions where it was stable before. Okay. So that is one of the key insights that you are getting from this discussion, that as the global temperature increases, the amount of humidity in near surface air also increases because of increased water evaporation rates because of higher temperatures. This can tip the balance in a conditionally stable region from a stable to an unstable condition, and you are likely to get more weather disturbances, more intense precipitation events. Also, the gradients are much larger between the between regions of low temperature and regions of high temperature as you change the as you increase the temperature of a parcel of air. So temperature gradients at high altitudes are also going to get exacerbated because of the increase in the amount of moisture and heat that is present in the parcels of air. So those are the two main takeout points on how global warming will perturb this kind of stability or instability systems. Okay. So next chapter that we will discuss is what we call the Earth-Sun relationship. It's a very important part of what determines the weather and the climate of the world. Okay. So Earth-Sun relationships include those parameters like latitude, longitude, Earth's rotation, Earth's revolution, axial tilt, eccentricity and parallelism. We will define all of these terms sequentially, that impact the average solar radiation energy flux in watt per meter square that is being received by a location on Earth at any given time during the year. Okay. So every location on Earth is getting certain solar energy in terms of energy per unit surface area, watt per meter square, energy per second per unit surface area. Okay. This is called the average solar radiation flux. All the primarily geometric and astronomical parameters that impact this average solar radiation flux per unit area that we are getting at a given location on the Earth is a part of Earth-Sun relationship. They include the latitude of that location, the longitude of the location, the nature of Earth's rotation and the revolution, the axial tilt of the Earth, and things like eccentricity and parallelism, which we will discuss. Okay. These are very important because almost the entirety of the energy in the atmosphere and the oceans is coming from solar energy that is being absorbed by the surface, by the air and by the waters. Thus, the extent and variation of this solar energy flux with time of day or seasons or years or even decades has a significant impact on the prevailing climate and seasons in a region. Okay. This is kind of obvious. So we will quickly go over certain basic things that you may have already learned in your school in terms of geography. We will just go over these so that we can have the discussion on those terms. So we will define some of the terms. The first term that we will be defining is what is called the solar irradiance. This is primarily the amount of energy that is coming to Earth from the sun averaged over the entire surface of the Earth. Okay. So there are several ways to explain this. First is, what is sun? The Sun is an average star whose mass is around 10 to the power 30 kgs and whose total radiation energy that is it is emitting per second is 3.9 into 10 to the power 26 watts, joules per second. So this is the total amount of energy that the Sun is emitting per second. It's a huge number. Okay. And the surface of Earth is around 6000 kelvins in temperature. Okay. Now the mean distance between the Sun and the Earth is around 1.496 into 10 to the power 11 meters. So around 1.5 into 10 to the power 11 meters. This is the mean distance between Sun and the Earth. And this mean distance basically controls the amount of solar energy that the Earth receives per unit time, per unit area, which is called the solar irradiance. Okay. This is the amount of solar energy that is arriving at the top of the Earth's atmosphere. Okay, because the atmosphere also absorbs some of it. Not all of this irradiance is actually hitting the surface of the Earth. So we will discuss that in later classes. Now, if you look at this picture, somewhere here is the Sun, far away, and the Sun is so far away that all the light rays are more or less parallel when it comes to Earth. The Earth is a sphere, but it is projecting a circle when the Sun is seeing it. So when we see the Sun, it looks like a disk. It's a circular projection of the spherical Sun, right? Similarly, when the Sun looks at us, for example, if you think of it that way, then the Earth also looks like a circular disk, which is this circular projection. And all the Sun's light is going through this circular disk. Okay. So what we see here is that the total energy of the Sun, which is 3.9 into the power 26 watts, divided by the total surface area at the Earth-Sun distance. So there is a spherical surface area, you can think, enclosing the Sun at the Earth-Sun distance. So if you divide that, you will get the solar energy per unit area at the Earth-Sun distance. Then we multiply it by this circular projection that the Earth is projecting towards this Sun, the total area, and that will give you basically the flux, okay, in watts. Okay. Now the average solar irradiance received by Earth on the top of its atmosphere is 1360 watt per meter square. So this cross-section circular projection area is receiving solar energy at the rate of 1360 watts per meter square. Okay. However, this energy is basically distributed over this circular area, which is basically pi r square. R is the radius of the Earth. Okay. An, which is the pi r square, where r is the radius of the Earth. However, this energy has to be distributed over the entire spherical surface of the Earth. In general, of course, only the lighted half, one hemisphere is receiving the Sun's rays, but if you average over the entire 24-hour period where the Earth is rotating and then do the per unit area measurement, then the total Earth surface is 4 pi r square. R is the radius of the Earth and the surface area of is sphere, so it's 4 pi r square. And this solar irradiance of 1360 watt per meter square is being distributed over this area. Okay. So the total energy the Earth receives is 1360 into pi r square divided by 4 pi r square, which means 1360 by 4, which is 340 watt per meter square. It may change a little bit from decade to decade. So in some decades this is a little bit higher, in some decades a little bit lower, because the Earth-Sun distance is not really fixed. It can change a little bit, okay, over long periods of time. Anyways, this is the average solar insolation at the top of the atmosphere when we are dividing it over the entire spherical surface 4 pi r square of the Earth. So Earth on average at the top of the atmosphere receives 340 watt per meter square of solar energy flux. Okay. So this is the average. This will have a significant variation depending on the location on which that flux is falling. So to understand that variation, we have to understand the parameters on which that variation depends, namely primarily latitude and then other parameters like longitude, etc. are also important. Okay. So what is latitude? Okay. Now, since the Earth is spherical and it is rotating around an axis, this axis is the north-south axis, north pole and the south pole, and a straight line through this is the axis of the Earth around which it is rotating. Okay. Now, we consider a plane which is perpendicular to the axis and divides this axis into two halves. Okay. So, the distance between the north pole and this point here is the same as distance between the south pole and this point here. So, we are imagining an imaginary plane perpendicular to the axis which is bisecting the axis. Okay. This imaginary plane is called the equatorial plane, and where it hits the surface of the Earth, it creates a circle, and that circle is the equatorial circle or the equator. Okay. So, we have defined the north pole, the south pole and the equator. Alright. Now, you can also generate other planes which are perpendicular to the axis at equal distances along the axis line. So, you can create a plane here, you can create a plane here, you can create more parallel planes which themselves will subtend circles on the Earth's surface. And all of these planes are parallel to each other and perpendicular to the north pole, south pole axis. Okay. These are all called latitudinal planes, and the circles they subscribe on the surface of the Earth are called latitudes. So, we have the equator, we have the latitudes. Okay. Now, how do we define these latitudes? So, suppose you have a latitudinal plane like this. It is there is a circle that is generated on the surface of the Earth because of this latitudinal plane. Now, any point on this circle you connect with the center of the Earth. Okay. And you connect any point on the equator with the center of the Earth. Okay. The angle between these two lines, the line connecting any point on the circle, latitude circle with the center of the Earth, and the line connecting the equatorial circle with the center of the Earth, the angle between them will be a constant value regardless of which point you choose. And this constant value helps us to define that corresponding latitude. So, here that angle is 45 and the angle is going in the anti-clockwise fashion. So, it is called 45 degree north. Okay. Similarly, this angle here is 30 degrees and the angle is going in the clockwise fashion from the equator to the latitude, and so this is 30 degrees south. Okay. So, every latitude has a unique angle from 0 to 90 degree north and 0 to 90 degree south, and that based on that we are defining the latitude circle value. Okay. Now, because the Earth rotates around its axis, during a rotation any point will only lie within its own latitudinal circle. So, suppose here is a point, it is Earth is rotating in the east-west direction, then as it rotates, this point will move along this latitude circle. So, all geographical points only ever move along its latitude circle during the rotation of the Earth. The direction along a latitude circle is positive in the east to west direction. So, if you move from east to west, that direction is considered positive and is called the zonal direction. So, east going towards west is called the zonal direction along a latitude, and it is a positive if it's east to west. If it's west to east, it's negative. Okay. Next, we will discuss longitudes. Okay. So, longitudes are nothing but a series of half circles on the surface of the Earth whose center is the center of the Earth. So, you take the center of the Earth, you draw half circles from the north pole to the south pole. Okay. And these lines are called longitudes. The longitudinal half circles are also called meridians or meridional lines. Okay. They are oriented perpendicular to the latitudes. So, this line, and if you have draw a latitude line, they are oriented perpendicular to each other. That is where they intersect, that angle will be 90 degrees. One latitude half circle is taken as a reference and it's called the prime meridian, and it runs through the Greenwich in London, and it is given 0 degree as the default value, just as equator is given 0 degree as the default value. Okay. Other meridional half circles are defined in terms of the angle they subtend at the center of the earth with respect to the prime meridian. So here basically, suppose this is 0, you take a point here, you drop a perpendicular on the north-south axis, you drop another perpendicular from your preferred meridian, say 90 degrees west, to the north-south axis at the same point, okay, and the angle between them is the longitude angle if it's in the east to west direction, or if it's in the west to east direction, it's negative. Okay. Now, what is the import? The meridians are hence defined in terms of 180 degrees west and 180 degree east in terms of the prime meridian. So this is the 0 degree meridian. You can move this way and you make this angle here. So this is 90 degrees west. If you go in this direction east of it and you subtend an angle with the center of the earth, this is the 30 degrees east. Okay. So this way you can go from 180 degrees west to 180 degrees east with respect to the prime meridian. All points along a longitude are in the same time zone. Okay. So all points along the longitude are in the same local time zone. That is, all of these points experience the noon at the same instant of time, and all of these points experience things like sunrise and sunset simultaneously. So this simultaneity is important. For all of the points across a meridian, noon happens simultaneously, morning and evening happens simultaneously, midnight happens simultaneously. Now the direction along a latitude, so this direction along this latitude is called the north-south direction and is the meridional direction. So direction along a longitude circle is the east-west direction, it's called the zonal direction. The direction around the longitude circle, the north-south direction, it's the meridional direction. The intersection of any latitude circle with any longitude half circle is always orthogonal, and hence the longitudes and latitudes create an orthogonal coordinate system by which any point within the Earth's surface can be located. Okay. So we will stop here. We have defined longitudes and latitudes. We will see how they are used in determining the several climatic parameters and the corresponding effects in temperature, etc. in the next class. Thank you for listening. See you again in the next class. Goodbye.